noise on invariant manifolds for SPDEs, which of course everybody can read anyway, but anyway.
Take your time. I'm glad you are still here. I would like to first thank the organizers for the opportunity to speak. I was here 13 years ago in 1997. I thought I would come much often, but it took 13 years to be often. Okay, so thank you very much for being here today. So I would like to look at invariant manifolds for stochastic PDEs and how to approximate them when noise is small. So I will start with some examples to get motivated, and then I would like to see how small noise make an impact on invariant sets called invariant manifolds, and also look at the small noise's impact on foliations. Foliations are related to invariant manifolds. Well, so these are the two motivational questions that gets me to this set of work. Invariant manifolds are widely used in deterministic dynamic systems. They help us to understand the dynamics. Now, for random SPDEs or SPDEs, they are random objects defined by Michael Wilkner a couple of days ago. That means they are geometric objects. When you change the sample, you change the shape a little bit. When you change the sample again, the shape also changes. Now the question I was asked, and also I asked myself is, can you say something about the structure? Can you draw one? Well, it's hard to do that. Even for linear systems, for linear stochastic systems, or let's say for deterministic linear systems, eigenspaces are invariant manifolds, so we know that very well. For linear stochastic systems, well, we don't have eigenspaces, but we have something called oscillator space, which is a stochastic counterpart of eigenspaces. Even for oscillator spaces, it's hard to draw, unless you have a simple system like a diagonal system or a triangular system, but otherwise it's hard to do. So that means even for stochastic linear systems, those invariant manifolds are hard to draw, hard to obtain, hard to compute actually. So I'd like to see if noise is small, can we say something about the structure of the random invariant manifolds? Now the second motivation for my work is as you see, numerical simulations for SPDEs, the interest has been strong and it has been going up. Now we can compute the individual paths well. Okay, with individual paths you can compute mean and variance, and so forth. And so forth means other deterministic quantities that you try to understand stochastic dynamics. Now, question. Can you go beyond that to compute something that carries more dynamic information? That's the second motivation for my work. So what to compute? Okay. Now, well, certainly I cannot answer all those both questions, but these questions motivate my work. Okay. So I would like to. So my talk will touch bases with two issues here. Now the results will be presented in general Hilbert space, but it's much easier to look at examples in the simplest Hilbert space, R2. So let's look at this example, a deterministic example. This is a saddle because you have two eigenvalues, one positive, one negative. Okay, and the spectral gap is big enough. Okay, now we can easily write down the solutions. Okay, so you have two solutions here, and if you multiply x, y, you get a constant. Okay, so that means our solution paths are hyperbolas. If you take a constant 0, you have x equals 0, y equals 0. So this is a picture you know by MATLAB simulation here. Now the eigenspace, the stable eigenspace is the x-axis, and we call it a stable manifold, which is Ws here. Y-axis is the unstable manifold. Now these two sets are very important. X-axis is very important because our points on x-axis have the same asymptotic dynamics, therefore important, we give them a name, stable manifold. Our points on y-axis are also important, are also special. They share the same asymptotic dynamics about backward in time. Okay. Now, so that's why we have special names for x-axis stable manifold, y-axis unstable manifold. How about other solutions? Well, they don't have the same asymptotic dynamics. However, they approach each other if you start at the right points. Okay, so here comes the multifoliation. A foliation means a bunch of fibers put together that form a structure. Now, one fiber in the foliation is defined as the set of points in the physical space, or R2 here. The points on a given fiber, if you start your dynamic machine at two different points, but as time goes on, they are going to approach each other. So if you think, if you want to understand the dynamics, that's also one criteria or metric to quantify dynamics, right? So this is one thing I mentioned earlier. Now let's look at a stable fiber. A stable fiber means what? Means points, a set of the points from which orbits will approach each other with a given rate. Okay. Now, if I look at the solution, I try to subtract the two solutions to compute to see if they approach each other. Now look, if I take t part goes to infinity, this term will go to 0, but this will not. However, if I set y0 equals y0 tilde, then the whole orbit will approach each other when t goes to infinity, right? So that gives us one fiber. It's called a stable fiber because I do it for t goes to positive infinity. Now, unstable fiber means the points from which the orbits will approach each other when t goes backward in time. So this now these fibers are different from manifolds. However, they also give us information about dynamics. If you are in the same fiber, I can tell you are going to approach other either forward in time or backward in time. Therefore, these are important dynamic structures, tell us dynamics, right? So we are interested in doing this. Now, this is an example for deterministic system. Now, in this deterministic system, the fibers are straight lines. Okay, so this is what we call a foliation portrait instead of phase portrait you saw earlier. For linear systems, as you see here, manifolds are straight lines, fibers are all straight lines. For nonlinear systems, you expect curves or surfaces or more complicated structures, right? So let's summarize this. Okay, foliations or fibers actually classify points in state space according to their asymptotic behavior. Okay, let me summarize these two observations. Invariant manifolds divide state space into components, okay, and into subsystems. And therefore, it helps us to look at smaller parts and try to understand the dynamics better. Now, foliations do something different. The picture I showed you earlier are very different very different. These are not solution paths, okay? These are not solution paths. You don't see that. You don't see motions here, but rather they are the sets. On each of them, they have the same asymptotic behavior. Now, what's the impact of nonlinearity on manifolds? Before we look at the impact of uncertainty. So let's do it simply. Let's say we have nonlinearity in one equation, and without we don't change the x dynamics. Okay. Now this system is simple enough because I can find the solutions. And once you have solutions, and if you remember the definition, that a stable manifold means all the points on which only have the same dynamics when t goes to infinity, then I can find a stable manifold. This is a MATLAB simulation. This is a stable manifold becomes curved. It was x-axis. Now it's curved here. I don't do anything on x dynamics, so this W is still there. And once you have this manifold, you know the rest of the dynamics, at least locally. Now, how about the foliation? What's the impact of nonlinearity on foliation? Same system. nonlinearity here, I can write down solutions. I can write down the distance between two solutions because I want to see if they asymptotically approach each other, right? So I computed the distance between the two. So what's stable fiber? Can you recall the definition of stable fiber? So it says when t goes to positive infinity, and if I start at 2 points on it, it will approach each other with the same rate. Now look at this. If I take t goes to positive infinity, this guy will go to 0, so I don't bother with that. So that means x component will approach each other. The only thing I need to look at is the y component, or y components are approaching each other. So t goes to infinity, this guy goes to infinity, that's bad. This one is good. So I need this blue thing to be 0 in order to achieve my goal, right? Which means what? Which means the stable fibers must be the points on this curve, okay? And I did not do anything on x dynamics, so the unstable fiber is the same. Now, there's a big theory on foliation in deterministic dynamic systems, and these are some of the references that I'm familiar with. And actually, before 1977, there was some work on foliation. Okay, so let's sketch the foliation. Unstable fiber, x equals constant. Now the stable fiber means y equals minus 1/3 x squared plus constant. So these are the fibers, okay? And the stable fiber means if I start these 2 points, one here, then when t goes to infinity, I know they are going to approach each other. Now this is not phase project. This means these are not dynamic motions. This is a geometric classification of the physical or state space here. Now, let's get to infinite dimensions because I like to set this in SPDEs. Now, so let's look at an example 2, a linear PDE. Okay, I put a 2 here. Now, eigenvalues can be found, and the spectral gaps can be computed as well. Now, in this space, a natural Hilbert space is L2, which is separable. Therefore, we can use Fourier series. Okay. Now, once you use Fourier series, you have an infinite system of ODEs. Now, this is not a phase portrait because we cannot draw phase portrait in L2. However, this is a symbolic phase portrait to indicate the dynamics. Only lambda 1 is positive. Therefore, only U1 has positive dynamics here. For the rest of the modes, U2, U3 is they all decay to 0. So this is a symbolic phase portrait for an infinite dimensional linear system. So that means we don't have a fundamental change if you go from linear in R2 to linear in L2. Okay. How about nonlinearity? Oh, okay. How about foliation? We don't have much change in foliation either. If you just take U1 as one coordinate and the rest of the modes as the second coordinate, you don't see the fundamental change. So very often people say, wow, you have fundamental change from finite to infinite dimensions, but for linear dynamics from this perspective, there's no change. Okay. Now, how about the impact of nonlinearity in the infinite dimensional setting? Okay, let's look at the real Ginzburg-Landau equation. It's real because I took the coefficients to be real. Otherwise, it should be complex in the Ginzburg-Landau formulation. Now, for this one, indeed, there's a fundamental change because I cannot draw pictures. Okay. However, if you believe a symbolic picture, there is something there which is similar to the example I showed you for the nonlinear ODE in my example 1. Now, this foliation theory in Hilbert space or even Bartha space started quite early, almost a few years after the finite dimensional setting. David Rule's paper was in Hilbert space. It touches bases with foliation theory, and Mali did that a year later in the Bartha space without using coordinates. In Hilbert space, you have coordinates, but in Barrett space, no coordinates, which also says the foliation theory does not depend on coordinates. Okay, although in my talk, I will use coordinates. And later on, Chao, Liu, and Lu, and Bates, and his collaborators extended this theory, and more or less we have a quite good theory for parabolic nonlinear PDEs in terms of understanding foliation stable fibers and unstable fibers. Now, the question now is, how about if we have noise? We have a nonlinearity. How about uncertainty? Does that do something to the invariant structures that we have just talked about, foliations and manifolds? Okay. Now, what we can do is for small noise. Okay, if the noise is very big, then the structure may be destructured or may maintain, but that's not what I can tell today. But a small noise, we can address the question, how far is the random manifold away from the deterministic counterpart? I know the deterministic part there, when the noise is gone. Now if noise is small, can we say something about the structure? Remember, even for linear stochastic systems, it's hard to understand or draw or describe the invariant manifold. So noise is small may tell us something about the structure is interesting in that sense. So let's first look at the impact of noise on manifolds and then on foliations. Now, since Michael Rukla did a very good job 2 days ago introducing random dynamic systems, so I don't have to say too much. Just remind you that a random dynamic system in the framework of Ludwig Arnold and his collaborators has 2 components. Okay, one is the driving system, which means noise. The second one is the flow, and here we call it co-cycle. And so a model for noise means a driving flow, driving system. I think Michael called it a magic system. I prefer to call it a driving system. You have a probability space, okay, and you have a deterministic dynamic system, theta t, on that probability space, okay. Theta t is a deterministic dynamic system, okay. However, it preserves the probability p here, okay. It does not have to be ergodic, but it preserves the measure p, or p is the invariant measure. In other words, theta t also deterministic, but a measurable dynamic system with an invariant measure. Now, model for the system evolution means you have a flow. Okay, here we call it a co-cycle, which really means you have a mapping which satisfies this property 1, the co-cycle property. Now you see here, if theta s is gone, this really means the deterministic flow property. But in the stochastic setting, we cannot have that because of the driving system. So this is the only difference between the deterministic and stochastic dynamic systems. Now I should mention this. This whole business was a stochastic flow and co-cycle setting for SPDEs or SPDEs. Started with David Elworth and his students. The paper that I read first is 1983 about the discovery of the co-cycle properties. Okay, I think David has probably had papers earlier than that, but this is the paper I read. Now for SPDEs and some SPDEs, we can take a canonical version of the probability space. That means although you started with a probability space when you define your Brownian motion or other noises, actually we don't have to stick with that one. We can work on one that is more manageable. That means you work on the space of continuous functions. This was also mentioned in Michael Ruckner's talk. And this F, the sigma field is going to be generated by cylinder sets, which is also equivalent to the sigma field generated by the compact open topology in this C0. In the C0, there's a natural topology, which is called a compact open topology, defined by looking at the uniform difference between the two solutions at any compact interval. Now, in this P is the corresponding Wheeler measure. So that means whenever we look at SDEs and SPDEs, we can take this as our new probability space. And here we know we have a topology here, therefore we can do something more, or at least visually to visualize some paths. Okay, and the driving system for SDEs or SPDEs is just the Wheeler shift. And the Wheeler shift is better than the driving system I just mentioned. Wheeler shift is ergodic, okay, and so P is the invariant measure and theta T, but it's also ergodic. So it's better. It has more features that we can handle, we can use. Okay. Now, so let's get to the first issue about the impact of noise on invariant manifolds, small noise case. Now, this is just a reminder for why manifolds are important. They are geometric structures, carries dynamic information. Now, this is the general setup here. So we have I think this as a PDE. It can be more general as an evolutionary system in the Hilbert space. Okay. Now this A is a linear part, F non-linear part. Now here, there's a small epsilon here. Okay. Now this U, this stochastic part is in Stanowich. Okay, not essential but convenient. Okay. Now the reason I'm using this simple linear multiplicative noise is because I need to change this, convert this into a random PDE, so that I can use random dynamic system setting. Now, Franco Flandoli and his co-authors has worked to generalize this to a more general linear operator, and in that case, you can still convert those SPDEs into a random dynamic system. Okay, so this in principle should apply to those, but this one is clear. I can easily write down that system. So let's stick to this. Now, if I write f depends on u, it can depend on gradient of u. Okay, as long as the dependence is at the order lower than a, and that to me is more a technical issue. Okay, so let's stick only to a simple case here, and also for a dissipative system, often you do cut off, because for nonlinear dynamic systems, you do not expect global dynamics. You try to understand the local dynamics. So very often we do cut off. So in that case, we usually ask for local Lipschitz, but after cut off, you have a global. So in my presentation, I may have a global. I may use a global Lipschitz condition. That cutoff is okay for dissipative systems, okay, like Wilkins-Bug lambda or other more physical models. Now the linear part, remember in my example 2, I said a saddle. When you have a saddle, you have a stable and unstable manifold. Here I need some saddle property as well. Saddle means you have one direction grow and one direction contract. Okay, so this in this Hilbert space setting, this saddle property is expressed in terms of exponential dichotomy. So that means in one direction, the system is grow at a linear level. In the other, it contracts in one direction. Okay. Now, random invariant sets. Now, random invariant set is a set depends on, is a geometric structure depends on sample. When sample changes, the shape may change. A random manifold, a random stable manifold, is a random set, but it has a dynamic feature near a reference point or a fixed point that you are working on. Because remember, we look at the local dynamics, right? So you must have a reference point you work in. So So in this, very often we would like a manifold to have a smoother or slightly smoother structure so that we can do, if not calculus, at least we do some analysis. So this Lipschitz condition is what we really need to for doing some analysis, right? So this manifold can be smoother, okay, C1 or C2, but otherwise at least Lipschitz, right? Okay. So we remember in my example 1, manifolds are curves. Okay. Here we also write this as a curve or a surface in the Hilbert space. Yeah. Now here I should mention is in Hilbert space or separable Hilbert space we have coordinates. So we can pick this. We can pick some coordinates as the stable part and the rest as unstable part at our own discretion. In other words, this stable and unstable is not strictly stable in our ordinary sense. As long as you can divide the spectrum into 2 parts, you call one stable and the other one unstable for convenience. In applied problems, you may really have real stable and unstable decomposition. Okay. And we also have unstable manifold as well. Impact. Okay. Now this is one theorem. Suppose epsilon the noise level is small, which means epsilon is very small here. This is not. This should be Brownian motion. Linear part, we have a saddle property, which means exponential dichotomy. Nonlinear part, we need it to have a second order Fisher derivative. The reason I'm doing that, using that, is because I'm going to do the Taylor expansion. So if you want to do higher order Taylor expansion in epsilon, you would need some stronger condition than this. Okay. In fact, if you would like to have a better estimate about your remainder term in your Taylor expansion, you would need some more condition. So let's just put a minimal condition here, and to go through what we need to do here. In example 1, I mentioned the spectral gap. In finite dimension, that's not a problem because you always have a gap there. But in the infinite dimensions, spectrum or spectral set may contain continuum. So, but to do manifold business, we need a gap condition. Okay, so that means if you have a gap big enough in your spectral set, and this should work. Now, this also says if your gap is not big, then you need your nonlinearity to be good in order to compensate this business. Good means flat, which means Lipschitz condition very small. So either way, this would be fine. Since Lipschitz condition is usually not small for a nonlinear PDE, so you better ask a gap condition to be bigger. So this is the limitation for this theory. You need a gap condition, which is not very strange from a dynamic systems point of view. If you don't have 2 distinguished directions, you can probably you may not be able to do manifolds. You will have to try some other ways to decode the dynamic systems. Okay. Okay. Now, second part of the theorem says we have, in this case, we have an invariant manifold, which can be described as a graph over the stable part. Now, the unstable manifold will be a graph on the unstable space. Here is the graph on the stable space, which is here. Now, what's the impact of noise when noise is small? So what we did is to do a Taylor expansion, a normal trick in perturbation studies. Now, the first part, when epsilon is very small, when epsilon is 0, certainly we should have a deterministic manifold. Otherwise, your theory is wrong or your derivation is incorrect. Now, the first order correction. Now, this is the term that we try to understand. This is the remainder term. It's in order of epsilon 2. Now, we did not write a uniform bound or almost sure bound here because that would require your nonlinearity to have a better second order or third order or second order Fisher derivative. Okay, so that can be achieved if you impose conditions on your nonlinearity. Now this H1 term or HD is right here. This is the equation called the Lyapunov-Perron equation. It's an integral equation. This U0 actually depends on UD. So this is an integral equation which gives us the graph for the deterministic manifold. A curve. Think about a curve. This equation is normally not solvable, even by hand or even by approximation. So very often this part is done numerically in the finite dimensional case. In infinite dimensions, you can do, with the gap condition, you can do Bollinger contraction mapping and do a iteration, but again, it's very hard to do that. Yeah. But what we are trying to do here is not to try to say some information about the deterministic manifold. Rather, we try to understand if noise is small, what is the change on this guy in the manifold. So that means we try to understand the correction term here, H1. Now H1 can be written in terms of a explicit form. You don't have to read out this. The point here is all these terms, this I is identity matrix, identity mapping, and V is in terms of everything new. PU is the projection in the Hilbert space on the unstable eigenspace. So that one is defined. And A is the linear part. This is the semigroup for the linear part. So that one is computable in theory. This is a Fisher derivative evaluated at U0. What is U0? U0 is the deterministic solution. It's the solution for the deterministic PDE when noise is gone. So that one is also null from a stochastic point of view, because I want to see the impact of noise. So assume you have a deterministic stuff there. Okay, so U0 is null.
Is U0 defined for all terms?
U0 is defined for parabolic equation for all future time, positive time. Yes, positive time. Okay, and this one, this one is Fisher derivative, ds, and this is also very complicated. Also, in principle, is computable. Okay, now B was B, and B plus Z. B is also computable. Now what's Z? This Z, this is a different Z. This Z should be the same Z. This Z is the stationary solution for the Einstein-Uhlenbeck equation or Langevin equation here. The same noise there, and this is a linear equation. Now this stationary orbit is null. And we used that to do the Dawes-Sassman transformation. And Ben Gordis did a Dawes-Sassman transformation in the first day of the seminar. So this Z is used to do the Dawes-Sassman transformation to convert SPDE into a random dynamic system. And this one is null. And I can tell you the form in the next slide. Okay. So C is also computable. So it's all computable in terms of what? In terms of deterministic information. Remember, I wanted to see what my noise do to your deterministic stuff. So I have to write everything in terms of deterministic dynamics. Okay. This is work of a PhD student son. Okay. This way. Now this looks formidable, right? This all involves deterministic information, but it also involves the computation of integrals in terms of the stochastic processes here. Look at this Z. This Z is a stationary orbit for a linear stochastic PDE in the Hilbert space. So this can be quite complicated. And now, if we can estimate something or evaluate something in simple examples, it tells us something. Okay, so in the future, if we can develop good ways to estimate these terms, then that will tell us information. Or if we have a way to compute it, that will also tell us information. Now, this is a good time to point out the important references here. Muhammad, Zhang, and Zhao. Muhammad is here, Zhao is here. And together with Lu and Schumacher developed the invariant manifold theory for part of the theory for stochastic PDEs. Muhammad is here. Are you sleeping there? Okay. Okay. The Zhao is here too. Huaizhong Zhao is here. For invariant manifold. So for some SPDEs, this kind of theory there for invariant manifolds. How and when you have a invariant manifold. Now approximating invariant manifolds, and we also have a Dirk Bolomka here, sleeping in my talk. Okay, and Dirk and Wang developed an interesting theory, and Dirk and his co-authors developed an approximation theory for center-like manifolds. But here we are doing this for other manifolds and fibers here. So what I'm presenting here is a perturbation theory for small noise. So in perturbation theory, what you need to do is to show your expansion is possible, which means you need to show some derivatives indeed exist, and also the remainder terms are manageable. Otherwise, your expansion is incorrect. So that's the major part of the proof. So solution, remember I only use the solution for the deterministic part, so we have a theory available to understand the solution. The estimates regularity is used in the second part to verify that U indeed has Taylor expansion in epsilon. Okay, now finally in the step 4 is the estimated remainder term. If your remainder term blows up, your expansion is wrong or renders not useful. So for that part comes from nonlinearity. Okay, so that means you need a nonlinear condition on the nonlinearity in your original equation, capital F in my setup. So that means if you have higher order derivative, and if your derivatives are well behaved, your expansion, your remainder term is well behaved. That's what the Taylor theorem says. And here, the only difference here is we do it in the Hilbert space. That means you use the Fisher derivative. Okay. Now, let's look at an example to see what this derivation says. Again, it's much easier to work in a simple Hilbert space R2 rather than L2. So the same equation in my earlier examples, but with a linear multiplicative noise here. Okay. Now these two equations are coupled. Okay. So we can let's use the scheme that I just presented and see what the noise. See what the noise does to the stable manifold. We can either do to unstable manifold, but let's look at the stable manifold here. When epsilon equals 0, we had in my earlier example, actually example 2, we have the manifold y equals minus 1/3 x squared. I might have the picture here. This is 1. So when epsilon is 0, we have the stable manifold here, parabola here. Okay, no noise here. Okay. Now, if we have noise, small noise, what can we say about the change on the manifold? Do it this way. Now, by using the derivation, calculating all those complicated terms, remember I only needed to get to the first order correction term. In this simple example, it works out. Okay, so this is the manifold. The random stable manifold has first term deterministic part, no problem. Second, the first correction term is in terms of this integral, and this is Brownian motion started in the system. I think in my system I use the W, here you use the B, but they're the same thing, sorry. So this is the Brownian motion. This is higher order terms. Now if we look at the graph, now this graph is hard to draw, right? With one sample you have one graph. With another sample you have the second one. But however, we human beings are very good at understanding mean and variance. So let's do that. So let's compute the mean here. Now if you compute the mean at the order of O epsilon square, now this term is gone. This integral has zero mean. So we still have the stable manifold. So with the accuracy up to epsilon square, the random manifold does not change at the mean level. Okay. Now if you go beyond that, you see the change. You see the subtle change here. So this this term does not have zero variance, right? Use the Ito formula, you get Ito isometry. You have the non-zero variance, which is this. So compute the variance of this term. You see the difference here. Now you see here. Now the variance is proportional to x to the fourth power, and this precisely says our theory is local theory, because when x goes very big, your area is very big, which is not surprising because this is local theory. Okay, and also surprisingly, this variance only depends on x, does not depend on y. Okay, there's some kind of homogeneity in the y direction here. Okay, so with the small noise, we have gained some understanding of the random manifold. Okay, that's why in homogeneity at the order of epsilon square, and also no change on the mean. Okay, so there is some change. Now if we can do more to understand the on each one term, we may be able. If we go to higher terms, we may be able to get other information at the higher moment. Or there are other ways to understand the random processes, right? Moment and mean are only one way to look at it deterministically, but there may be other ways to look at this. But this can be explored in some way, or maybe numerically even. Now let's look at a SPDE case in a real Hilbert space. Now again, it's the real Ginzburg-Landau equation. And I put a bigger linear term in order to have more unstable modes. If it's only one unstable mode, then the reduction is simpler. So in this case, we have if u, as you see here, I think I mentioned earlier, and then we need to go to a space, which is the domain of a fractional power of Laplacian, delta plus 10. But here I did not put in all the details here. So we have a separable Hilbert space with a basis, and this is H stable eigenspace, unstable eigenspace. With this stable and unstable eigenspace, we can decompose the Hilbert space into two components. Okay. Now this with the two components. HS, HU, we can compute the projection, PU and the PS, okay? But in terms of the scalar product in the Hilbert space H here, H is just L2 here. So this Fisher derivative can be computed, and U0 is the solution for the corresponding deterministic equation. So this in principle, this is computable. Now this manifold can be computed here. Each term is computable in principle. Now remember, my second motivation is try to see what kind of things we can compute for stochastic PDEs. Go beyond computing individual paths. Okay. Now this is one thing that we may be able to compute the stable manifold up to some approximation order. So this one, we don't have a clean formula for this. However, it is a manifold for numerical simulation. Now the second part is much shorter because I use the same setup as in the first part. So as you see in the earlier part of my talk, you know the foliations are important. It's a different geometric structure, but they tell us dynamics. Now, if noise is small, can we say something about the fibers in the foliation? How much does the noise do to modify the fibers? Now, in the random for the theoretical part, for foliation for random dynamic systems has been going on for the last over a decade now. This Tom Waller started with finite dimensional foliation business, and all of this book collected that part of the work. However, the theory is very complicated because it uses a random norm, which is hard to manage. Okay, that means you use a meter. The meter changes from sample to sample, so it's sometimes hard to visualize. Also, the theory is beautiful; it's hard to visualize it. But in the theory that we are doing here, we have a fixed metric, so that offers something useful from our perspective. For the SPDEs, Lu and Shimafos just published a paper recently on this counterpart in the infinite dimensions for some SPDEs. Now the problem is all the fibers in foliations look extremely complicated. Can we say something? Can we try to understand something when noise is small? That's what we're trying to do here. Okay. Now this is the start point. From the setup in Lu and the Shimafos, this random fiber, well, fiber goes through a point. So this is the reference point. A reference point at this fiber through this reference point can be written in terms of these two terms. Well, the first term is nothing; it's just a projection. So the only second part is what we care about here. This psi is coming from this equation, and this is something like a Lyapunov-Perron equation here. So if we can approximate psi, then we may be able to approximate LS. That's exactly what we do here. Now this Z is the stationary solution for this Langevin equation. Yeah, this one is also is explicitly given here. Okay, so what we are going to do here is to approximate this psi from approximate the solution of a Lyapunov-Perron equation. But here is not quite the Lyapunov-Perron because we on each fiber of the foliation we like to see those two solutions approach each other. So this is actually is a subtraction of those of two Lyapunov-Perron equation. Okay. Now, for epsilon small, we have the approximation. The first term, the main term is the deterministic fiber. Correction term is written in terms of this of our known information, actually our deterministic information, except the Z. Z is a stationary orbit that I used in the Dawson-Sussman transformation. Okay, that's the only part which is not completely related to the deterministic system. Now it's all in terms of the first order Fisher derivative. The second order Fisher derivative will be used in the estimation of the remainder term. Okay. Okay. So let's look at the example. Yeah, look at this example. The fibers, the stable fibers for the deterministic system. Do I have a picture for this? I don't have a picture for this. Okay. Now for deterministic system, when everything is zero, deterministic system, the fibers are parabolas. I showed you in the earlier picture. Those fibers, each fiber on each fiber, system orbits approach each other. Now on this deterministic, on the random case, the fiber looks like the following now. For this simple example, is computable. Epsilon although this is very complicated here, but it's all computable. This X hat is the solution for the deterministic system. Well, it is at a constant because the deterministic fiber has a constant as well. This Z is computable here. So this one, if you do variance or moment analysis, you also have some information about the first order correction term. Now for the PDE case, okay, for the stochastic PDE case, this we won't be able to get this far. However, we can numerically compute. So what I'm saying here is to touch base with my first slide. So it might be possible or interesting to evaluate this kind of approximation in order to get some information about the foliation for SPDEs, and probably it also gives us some insight about what we should compute once we know how to compute the individual paths. Okay. So I will not show you an example for SPDEs. Okay. So this concludes my talk. It has two components: impact of small noise on manifolds and foliations. Thank you very much for your attention.
Questions?
Yes. You mentioned the word of the talk of Goldis. Do you think it would be important to perform similar analysis for the problem he presented?
Yeah. So in Bangladesh, you transformed a more complicated noise into a random PDE, right? Yeah. So if we can, for a more complicated SPDE, if we can convert into a random PDE, therefore we have a random dynamic system, then it's possible and it's interesting to me, yeah, in my point of view. Yes. We can talk a bit more.
Sure.
Do you think it's possible to extend the your representation of the error term to on time interval to see the time evolution of the manifold?
Aha, time evolution of manifold. Hadn't thought about that. Maybe possible. So the manifold is a sample-wise thing, right? So when you mean time and interval, so you mean what? You mean a manifold is a local manifold. Therefore, it's for finite time, right? Yeah. So it might be possible to go beyond that. So even though our theory may not tell us a lot for the time interval, it's also finite. Might go beyond a little more. It might be possible, yeah.
Tyler?
How important is the global Lipschitz condition that you have to get the global manifolds?
Oh, right. Global. Yeah. Okay. So here we have a
Non-linearity.
Yeah. So here we use the global Lipschitz condition to simplify the analysis. For a dissipative system, when you have a tractor or random tractor, you do cut off. So since the expansion is fundamentally local, so that condition is not a problem, right? Because you will get to local anyway. Yeah. However, one limitation is this: if the nonlinearity depends on gradient, then I need a more stringent condition on the Fisher derivative. That might be what you referring to, yeah.
Because you have in the examples you have a U cube. You have
yeah.
They are not.
They're not limited at all. yeah. So that's what I said. We need to work on the fractional domain of fractional powers of Lagrange. Yeah.
Other questions?
I have another question. Is it okay? One more. Is there a large deviations for this?
Large deviation.
Is your
So large deviation is another way to understand the impact of noise. Yeah, this is recent work. The recent work is for the SPDEs. Yeah. So large deviation is another way to understand the impact of noise, but at the level of individual paths. Here is at a geometric structure. Good point.
Anything more? Well, let's thank Jinqiao and all the speakers for this.